A geometric series requires you to add the terms of a geometric sequence. We have two formulas for this, and either one works. We say S subset n, or S subscript n, is equal to u1, or our first term, times the quantity 1 minus r to the n divided by 1 minus r, or conversely, we could use the one in red on the right. S to the n is equal to u1, our first term, times, instead of 1 minus r to the n, now we have r to the n minus 1 divided by r minus 1. It's customary to use the formula that gives us a positive denominator. So if our common ratio is greater than 1, we'd want to use the one on the right, because that will give us a positive denominator. If our common ratio is between 0 and 1, we use the one on the left to also give us a positive denominator. Here's a very straightforward example of the application of the geometric series formula. Find the sum of the first 27 terms of this sequence, 2, 6, 18, 44, 32. Well, our first step is to figure out what kind of a sequence is it. 6 divided by 2 is 3, 18 divided by 6 is 3, 45 divided by 18 is 3, 132 divided by 44 is 3 as well. Or we could say 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 44, 44 times 3 is 132, etc. So I know I have a geometric sequence. Well, to get the sum, or the series, the sum of the geometric sequence, which is the series, I use this formula. S to the n equals u1, which we know is the first term, times the quantity r, which is our common ratio, which is 3, to the n, which is the number of terms we're interested in, minus 1, that's in parentheses, divided by r minus 1. We're using this because when we do r, our common ratio, 3 minus 1, we get a positive denominator. Our first term is 2, so I plug that in. Our common ratio is 3. We're interested in the 27th term. Put that there. Minus 1. The whole 3 to the 27th, get that answer, minus 1 times 2 divided by 2 gives us 7.63 times 10 to the 12th. Another huge number. We can now talk about a convergent geometric series. If the common ratio r of a geometric series or sequence is such that r is between negative 1 and 1. Notice it's not equal to negative 1 and it's not equal to 1, but it's between negative 1 and 1. So it's a fraction, it's a positive or negative fraction between negative 1 and 1. Then the terms get smaller and smaller as n increases. For a geometric sequence or series where our first term is 2 and our common ratio is 0.5, I can, given this information, I can write out what the sequence looks like. We start at 2, and our common ratio is 0.5. So 2 times 0.5, or 2 times 1/2 is 1, times 1/2 is 0.5, times 1/2 is 0.25, times 1/2 is 0.125, times 1/2 is 0.0625, etc., etc. You can see our numbers are getting smaller and smaller and smaller. Well, what happens when I take this sequence and I make it into a series, and instead of having these commas here, I change those for plus signs. So I'm adding that to that, to that, to that, to that. I hope you can see that we're going to get a finite sum, or our sum is going to be going towards some finite number. It's going to be approaching, or the limit will approach some number. When we saw where our r values were greater than 1, as we increased down the line of this series, our total sum was getting bigger and bigger and bigger, and we got some very huge numbers for the sum of 53 numbers and the sum of 27 numbers. Now we see that this is going to be going towards some finite amount. So here is an example of the formula of the geometric series where the common ratio is between negative 1 and 1. We know this is the old one that we've seen. The sum of n terms is our first term times 1 minus r to the n divided by 1 minus r. Why do we choose this one? Because if r is between 1 and negative 1, then this will give us a positive value for r, provided r is positive, between 0 and 1 actually. Well, if we use this one, and we plug in an r of, say, 0.5 there, an r of 0.5, if we want to find the first 50 terms, some 0.5 to 50 really goes to a very, very, very small number. So 1 minus a very, very small number can be approximated by 1. 1 times u to the 1 is simply u to the 1. So for a convergent series, which means our r is between negative 1 and 1, this is our formula. because this whole part of our original formula collapses to 1. For example, for the sequence 10, 5, 2.5, 1.25, 0.625, find the sum of the first 100 terms. Well, 5 divided by 10 is 0.5. 2.5 divided by 5 is 0.5. 1.25 divided by 2.5 is 0.5. 0.625 divided by 1.25 is 0.5. So we know that our common ratio is 0.5, which is between -1 and 1. So to find the sum of the first 100 terms, I write my formula here, which is u1 times 1 minus r to the n divided by 1 minus r. And we can see when we plug in for our first term, our common ratio, the number of terms we want, and then 1 minus our common ratio on the bottom, that 0.5 to the 100, as I've got down here, is 7.89 times 10 to the negative 31. In other words, this is so small that this whole number set in parentheses can be approximated by just 1, because 1 minus a extremely small number is going to be about 1. If we're talking in 3 sig figs, which is the IB likes, it's still going to be just 1. So what's 10 times 1? This can be approximated by 10 times 1 divided by 1 minus 0.5, which is equal to u1 divided by 1 minus r, which is what we had before. Here is the final statement on all of this convergent series stuff. We have our formula Sn, or the series sum for a geometric series of u is equal to u to the 1 times, or this is our first term, times 1 minus r to the n divided by 1 minus r. This, as n goes to infinity, gets larger and larger and larger. In our last example we saw that was equal to 100. R to the n goes to 0. So this term, as n gets bigger and bigger and bigger, this term here goes to 0, so we can approximate this as 1 times that, which is u to the 1, or our first term divided by 1 minus r, and we can get an infinite sum of infinite terms.